Bismillahirrahmanirrahim. In this video, we'll discuss about linear DC machine, and we'll also try to explain example 1.10 already solved in the book. Now, a linear DC machine does not rotate, rather it slides on a rail. So, if you have a rail like this and there's a bar, this bar will slide up and down or right or left depending on the arrangement of the circuit or the current flow through the circuit. A linear DC machine consists of a battery, a resistance to control the current, connected through a switch, and a pair of smooth frictionless rail. So these are the rails as shown here, or this rail. Along the bed of this railroad track is a constant uniform density magnetic field directed into the page. So the magnetic field is directed into the page, so just like this missile is directed into the page and the back is cross. So these crosses means that the magnetic field is directed into the page. If you look at this diagram, then the magnetic field is coming from top to bottom, or the north is here and the south is here. A bar of conducting metal is lying across the track. So this is the bar of conducting metal as shown here. Now, before we go into solving the problem, let me clarify left hand and right hand rule. There is a lot of confusion on the net about left hand rule and right hand rule. I'll make an effort. The left hand rule is used for motors. Let it be clear. Some people say it is the same. No, it is not the same. But let's be clear that we'll use left hand rule for the case of a motor. And as you can see in this direction, if the current is flowing from here down here, then we have to determine the force. So if we use this method, and since this diagram does not represent exactly what we have in our case, the field is into the page or into the screen, so I have used my finger. So this is representing the field, and the middle finger is representing the current. So the current is going down, and therefore the force will be on the right hand side shown by the thumb. So this is the case that in case of a motor we use the left hand rule to find the direction of movement. But in case of a generator, now here it is a generator, it is being pulled by some kind of a force. So in case of a generator, we need to find the direction of the current in the bar, and for that we'll use the right hand rule. So right hand rule, again, this exactly does not represent our diagram, so I have tried to draw it. So my this finger is towards the field inside the screen, and my thumb is pointing the force, so it is pulled towards right, and therefore the middle finger is showing the direction of current. So this is how the current will flow when the force is applied towards the right hand side. Let's see another scenario of generator. Now in this case, the pull is towards the left hand side, and then we have to find the current direction. Again, we'll use the right hand rule for the generator. So my thumb is showing the force, the second finger is showing the field inside the page, and therefore the middle finger is showing the direction of current. So in this case, now the current will flow towards the bottom, or from top to bottom. So if you keep this in mind, then all your queries about the direction of current flow or the direction of movement of the bar will be clear. Okay, now let's see the scenario when the switch is closed. A current will flow through the circuit, and so we can write by KVL equation. We start from here, so minus VB I into R, and this voltage induced E induced equal to 0. So we get this equation, and from here I can be written as VB minus E induced over R. Now, since the bar is initially at rest, E induced is 0. So initially, the moment we close the switch, the bar is still at rest. So since there is no movement of the coil or the wire or the bar in a magnetic field, therefore there will be no voltage induced. We know from the generator law. That means E induced is equal to 0. And so if we put E induced is equal to 0, then our current will be VB over R. The current flows down through the bar across the track. Now we have already discussed this about the direction of the current. It is, since it is going from the positive terminal of the battery, so this is flowing down through the bar. And we have a relation, or vector relation between force and the bar or length of the bar vector and the flux vector, which is given by this formula. F is equal to I into L into B. Now there is a confusion here, and let's be clear. The magnitude of the length, only we are concerned with the length that is from this portion to this, where the current is flowing, not the external portion. So this length is given by L, the magnitude is L. When we represent it in terms of a vector in the direction of current flow, it should have been capital L, but Mr. Chapman has used this symbol, which apparently looks like a current I, but it is not current I, it is actually length vector in this case. So we have to keep that thing in mind. Okay, that means when the current is flowing, a current flowing through a wire in the presence of a magnetic field will induce a force. And we know this from the motor action, that a current carrying wire in the presence of a magnetic field has a force induced. So there will be a force induced in the wire. And because of the geometry of this machine, the force induced will be equal to ILB. So this is, if we write this in terms of a magnitude only, then vector L will become this L small, and vector B will become B, simple B, not bold. So F induced will be given by I into B, L into B, and its direction, it says, will be right. We already have discussed this, but let's see again. Since it is a motor, so we'll use the left hand rule. The current is coming down, as we discussed that current is coming down. So current is coming down, and the field is into the screen or into the page, and therefore the thumb will show the direction of movement of the bar, and that is why it is moving towards the right. Therefore the bar will accelerate to the right, since we are applying a force to the bar, and therefore by Newton's law F is equal to ma, so there will be an acceleration, so the bar will accelerate. Okay, now let's see the scenario. When the velocity of the bar begins to increase, so this is moving on the right hand direction and its velocity is increasing, there will be a voltage. We know that when a conductor moves in a magnetic field carrying then there will be a voltage induced in it. So there will be a voltage across the bar. and this voltage induced will be dependent on the velocity with which the bar is moving, and it is given by this formula: velocity multiplied by B multiplied by length of the bar, and this is the flux. And its positive direction will be on the top, because this induced voltage will oppose the voltage which is causing the movement. So that is why it will be in opposition to this, and so there will be positive sign at the top. And now let's see this current equation. We have seen that the current is given by VB minus E induced over R. Now as E induced increases because of the movement, this difference will be reducing, and a point when E induced becomes equal to VB, this will become 0, and so the current will become 0. So we say that as E induced increases, the current I decreases. Now, as a result, I will become 0 when E induced becomes equal to VB. We already discussed this. So the net force on the bar will be 0, because force induced is dependent on current, and since current is 0, therefore net force on the bar will be 0. So what will happen then? Since the applied force becomes 0, hence there will be no acceleration, because we know that acceleration is dependent on the force. Since force is 0, so no acceleration, and the bar will now move with a constant steady state speed. So since there is no acceleration, therefore the bar will now be moving at a constant steady state speed. So let's now recap. E induced is equal to VB now at steady state, and also E induced is equal to V velocity BL. Now we have added a suffix SS, that means at steady state, that is the speed at steady state is VSS, and these two are equal, so we can say that VSS BL is equal to VB, and from there we can find VSS to be VB over BL. So this is the formula that we'll use to calculate the steady state speed for in these coming problems. Now this is the problem that we need to solve, and there are a lot of questions, so we'll take one at a time. So let's take the first one, first part, A part. What is the machine's maximum starting current, and what is the steady state velocity at no load? So two questions. Okay, at starting condition, the velocity of the bar is 0, so this is not moving, and therefore E induced will be 0. Since there is no movement, therefore the velocity is 0, and therefore the induced voltage will be 0. And so putting E induced equal to 0 in this current equation, we can find the current to be 400 amperes at the start. Now the second part, the steady state velocity. We know the steady state velocity formula, VB over BL, plugging in the values. 120, B is 0.1 Tesla, and the length of the bar, this portion only, which is shown by L, is 10 meters, so we plug in that, and therefore the steady state speed is 120 meters per second. Now the second part, suppose that a 10 Newton force pointing to the right were applied to the bar. What would be the steady state speed? Okay, so what is happening? a force 10 Newton is applied here towards the right hand side, and we need to find the steady state speed. So F applied is 10 Newton to the right. F induced, we know, is given by the formula ILB. The final steady state will occur when the induced force F induced is equal to the applied force, equal and opposite. So the applied force is in this direction of 30 Newton. Therefore, the induced force has to be of 30 Newton in the opposite direction for this bar to be in steady state condition. So we can say that F applied has to be equal to F induced, or F induced has to be equal to F applied, which is equal to ILB, which is equal to 30 newtons from this. And therefore, we can find the current at the steady state, F induced over LB. So we're plugging in the values. It is 30 amperes and has a current that is flowing up through the bar. Now, why it is flowing up through the bar, or how it is flowing up through the bar, for this we have to again go to the Fleming's rule. And since this is a generator, it is moving and producing a voltage, therefore it is generator, so we'll use the right hand rule. Now, what all is given is the force towards right, so thumb is representing the force towards right, the magnetic field into the screen or into the page, so magnetic field is directed into the page, and therefore the middle finger showing the current, which is current will flow up, so we are saying that the current is flowing up through the bar. And then the induced voltage we can find from this formula. We can either write it from this way or we can write it from this way. Since the current direction is from right to left, so I have started, or I'm writing from right hand side. So minus E induced plus IR plus VB is equal to 0. And from here we can find that E induced is equal to IR plus VB or VB plus IR. So plugging in the values of VB 120, I 30 amperes we got from here, and R is 0.3. So induced voltage is 129 volt. And so now we can find the new steady state speed. Induced voltage is now 129, the other items remain same, and so the steady state speed now is 129 meters per second. Then there are other parts of this question. How much power would the bar be producing or consuming? So let's see that. So the power produced by the bar is E induced into I, or actually this is produced due to movement of the bar. So E induced was 129 and current is 30. So the power generated is 387 watt of power. The next part is how much power would the battery be producing or consuming. So now this voltage is more 129, battery voltage is 120, therefore this is supplying to the battery. That means the battery is consuming the power. So the battery is consuming power and it is equal to 120 is the battery volt. Current through the circuit is 30 ampere. So the power consumed by the battery is 3600. The fourth part is explain the difference between the two figures. Okay, so let's see the difference. The difference between the two is 270 watt. And where is this going? This is being consumed by this resistor. So this is loss in the resistor. And then is the machine acting as a motor or generator? So we have learned that the induced voltage is more than the battery voltage, and therefore this is acting as a generator. And now part C. Suppose that a 30 Newton force is pointing to the left. So earlier it was pointing to the right. now it is pointing to the left, and so again we have to find the steady state speed and answer the question whether it is acting as a motor or a generator. So let's proceed in the same manner. This time the force is applied to the left, and therefore the induced force will be to the right. So this is the applied force, so induced force will be in the right hand direction. And from this formula that we learned earlier, that F applied is equal to F induced is equal to ILB. So F induced will be 30, and putting in the values of LB. In this case also the current is 30 ampere and flowing down the bar. Again, to find out whether it is flowing down the bar or up the bar, we have to use the right hand rule, Fleming's right hand rule. So what all is given? We have the we know that it is moving towards, or the force applied is towards the left, so this thumb is representing that force. The magnetic field is into the page or into the screen, and therefore the current will be moving down. So this is the direction of the current. So we can say that the current is flowing down the bar. And now the induced voltage we can find from the circuit. So E induced is VB minus IR. You can follow this KVL, minus VB plus IR plus E induced. And now plugging in the values, VB is 120 and I and R. So now the induced voltage is 111 volt, 111 volt. And now we can find VSS. So VSS is E induced over V by L. Plugging in the values, the VSS or the steady state speed is 111 meters per second. And since this voltage is less, induced voltage is 111 and the supplied voltage is 120, therefore this is acting as a motor. So the machine is now acting as a motor, converting the electric energy from the battery into the mechanical energy of the motion of the bar. And then part D and E involves the MATLAB plot, etc. So I will avoid this. If you are keen, you can just go through the book to understand how this has been done. So I hope this gives you an understanding of the basics of linear DC motor. Thank you.